I thank the organizers, in particular Professor Nandakumaran, for the invitation to give a talk in this very nice place. Professor Nandakumaran asked me to speak about oscillating boundary, homogenization of oscillating boundary. Then I do that. Moreover, I add some topics. Until now, you have seen linear problems. Then I will speak about nonlinear problems. Until now, we have seen equation. I will speak about variational inequality. And also, I add some perturbation on the boundary condition. Maybe, I don't know if a good target this. Anyway, I shall try to give very slowly. I don't know if I finish to say. Anyway, I give you the paper, there are all details. You can stop me in each moment. You can correct me if I'm able to answer where you answer, well, otherwise I go on. And I start to introduce the domain with oscillating boundary. With n, we denote an int in the now I give all the notation that we use in this now in the next lecture. With n, we denote an integer positive number, and n greater equal to 2. Then with x prime, we denote a generic element of R n minus 1. And while a generic element of Rn will be denoted by x prime, xn, then this belongs to R n minus 1 cross R equal R n n. Then xn in the sequel is the last direction. Moreover, with LA is a positive number. In the sequel, A means always above, AB always below. Okay? A positive number. With CB, we denote a continuous function on Rn minus 1, such that 0 is greater of C x prime for each x prime dot R n minus 1. And finally, we denote with omega prime a subset of R n minus 1, which supposes bounded, open, connected, set with Lipschitz boundary. Okay. Then we introduce these subsets. Sigma A x in Rn such that x prime is in omega prime and xn equal LA. Omega A x in Rn such that x prime is in omega prime and xn greater than 0 and less than LA. Sigma 0 x in Rn such that x prime in omega prime e xn equals 0, omega b x dot Rn such that x prime in omega prime and xn greater than psi x prime less than 0. And find omega equal omega A union sigma 0 union omega B. Then, for instance, in dimension 2, this omega prime, this is your function CB, this is LA, then this is sigma A. This is omega A. This is sigma 0. And this is omega B in dimension 2. With epsilon, now let us introduce the domain with oscillating boundary. With epsilon is a positive parameter taking value in a sequence, in a vanishing sequence. Okay? With small omega prime, a subset of the interval 0, 1, n minus 1, well contained in 0, 1, n minus 1, with bounded open connected set with Cm plus 2 regularity. Later, we explain why we assume that this regularity on the boundary of small omega. Then we denote by Q epsilon the union of K in zeta n minus 1 such that epsilon omega plus epsilon K is well contained in omega prime of epsilon omega prime plus epsilon K 0 LA. Excuse me, here Cm plus 2 regularity with m greater than n minus 2 by 2. I forgot this. Then what do we take here? We denote by omega A epsilon, omega A intersection Q epsilon, with sigma A epsilon equal sigma A intersection Q epsilon, sigma 0 epsilon equal sigma 0 intersection Q epsilon, sigma A lateral epsilon equal the boundary of omega A epsilon minus sigma A epsilon union sigma 0 epsilon. And omega epsilon equal omega A epsilon union sigma 0 epsilon union omega b. Then I make a picture in dimension 2 for this. This is always omega b. This is LA. Okay, this boundary, the top of this teeth, we call it sigma A epsilon. Okay? Sigma, the lateral boundary of the teeth, is called the union sigma A lateral epsilon. This part sigma 0 epsilon. Then omega A epsilon is the union of the teeth. A omega epsilon is all this set, okay? Then when epsilon tends to 0, the thickness of each teeth becomes smaller and smaller, but the number of teeth increase. Roughly speaking, these teeth fill this region, okay? Then this is our domain. I consider in periodic oscillating boundary. We have also considered some non-periodic oscillating boundary. You can find something about a non-periodic oscillating boundary in the paper, my paper with Olivier Guibe and François Murat. When we consider, of course, we have some assumption, but not periodic. In this sequel, if we have a function defined on this domain, we denote, suppose that V a function defined on omega epsilon, we denote with V tilde the Z extension of this function in omega A outside the teeth. Okay. When we introduced the domain, for introducing the problem that we want to study, I have introduced some function. In the sequel, P is a number in Q plus infinity, excluded plus infinity. Poi A is a function of x, c, defined in omega. Omega is all this is omega, all the domain. Cross Rn. This is a vectorial function, valued function A. The x c is equal A1, the x c, A n minus 1, the x c, A n the x c, then belongs to Rn. We denote this by A prime the x c, A n the xc with a prime, we denote the first n minus 1 components. Which is the assumption on this function a? A is a Kara-Theodori valued function. What this means? That is measurable in x for every xc, and is continuous in xc for almost every x in omega. We assume that a of x as a function of the second variable is strictly monotone for almost everywhere x belonging to omega. What this means that A is strictly monotone in the second variable, that A of x c1 minus A of x c2 inner product with c1 minus c2 is greater than 0 for each c1, c2 in Rn. And this equals 0 if and only if c1 equals c2. Okay? For almost everywhere x in omega. Moreover, we assume that IA is a strictly coercive function in C. What this means? There exists alpha greater than 0. There exists a function F1 in L1 of omega such that alpha modulo norm of C to power P plus A1 of x is less than of A of x C for every C in Rn and for almost everywhere x in omega. In the sequel, we call this condition coerciveness condition, okay? Moreover, we assume that A is p-grouped. What this means? That there exists beta in 0 plus infinity, beta 1 in LP P minus 1 over omega. This is the conjugate exponent of P, such that the modulus of A of x C is less than 1 beta mod of C to power P minus 1 plus beta 1 of x for every C in Rn almost everywhere x in omega. Beta is in L1. Beta 1 is in L1. Okay, in the sequel we call this condition the growth P condition. Some example. For instance, P is less than 2, greater than or equal to less than plus infinity. You can take A of x C equal G1 of x, the modulus of C to power P minus 2 C plus G2 of X, where G1 and G2 measurable function, G1 and G2 from omega, G1 from omega in R, G2 from omega in Rn are measurable function, G1 of X greater than C1 greater than 0 and less than C2, almost everywhere in omega, and G2 in L, P minus 1 omega to power n. For instance, exercise prove that this function satisfies this condition. If P equals 2, you can take A of X, C equal A of X, C plus G2 of X, where A is a matrix-valued function, X belonging to omega, assume A of X in R n cross n. G2 is a function X belonging to omega sin G2 of X in Rn. A of X, C is greater C1 modulo of C to power 2, where C1 is a positive constant for every C in Rn, and almost everywhere X belonging to omega. The modulus of AEG of X less than or equal beta, almost everywhere X in omega, for every EG equal 1 n, and G2 in LP P minus 1 omega to power n. Okay, this is the first function we introduce, this vector valued function. P equal 2. Ah, okay. Sorry. Thanks. Yes, P equal 2, then is. Yeah. Thanks. The conjugate exponent of 2 is 2. Okay, poi let us introduce another function, H0, omega cross R in R. Allora, H0 is a Caratteodori function H0 is monotone in the second variable for almost everywhere X in omega. Monotone means that we required only this, the first condition, okay? Not the second one. Moreover, we don't assume coercivity, we have not coercivity assumption on H0, but only grouped P condition. That is, there exists gamma in 0 plus infinity, gamma 1 in LP P minus 1 omega such that the modulus of A0 dxc is less than gamma, excuse me, xt, we call t the second variable, modulus of t to 1 p minus 1 plus game 1 of x for every t in R and almost everywhere x in omega. Then we have not only growth condition, not coercivity condition on this function. For example, if p greater or equal to less than plus infinity, we can assume you can choose h0 of xt equal g3 of x, the modulus of t to power p minus 2t, plus g4 of x, where g3 and g4 are functions from omega to R measurable, and g3 of x greater than or equal to 0 less c, almost everywhere x in omega, and g4 in LP p minus 1 omega. You remark here you can choose G3 equals, for instance, you can choose G3 equals 0, G4 equals 0, and then H0 can be 0. Or you can choose G3 equals 0 and G4 equal a constant, and then H0 is a constant. On the other side, for A, you can, A cannot be 0, it cannot be a constant. Okay? Okay, the last function that we have to introduce. H, a function from omega A cross L in R. Then H is defined only in omega A. A is, for instance, for exercise, you can verify that this function satisfies this condition. A is a continuous function. A of x point is a monotone for almost everywhere x in omega A. But we assume growth condition x eta in 0 plus infinity, eta 1 in W1 p minus 1 p omega E, such that the modulus of h of xt is less than or equal eta modulus of t to power p minus 1 plus eta 1 of x, almost everywhere x in omega A for every t in R. Moreover, on this function, we suppose also that admit derivative, and we have some assumption on derivative. The gradient of h is a categorically valued function. There exists theta in 0 plus infinity and theta 1 in LP p minus 1 omega E, such that modulus of derivative with respect to t, the h of xt less than theta modulus of t power p minus 2 t plus a constant. No, only, excuse me, modulus t p minus 2 plus a constant. And the derivative with respect to xi of h of xt is less than theta modulus of t pi minus 1 plus theta 1 of x. For almost everywhere x in omega A, and forever e equal 1 and minus 1. For example, you can take h of t equal a constant, or h of t equal t, or you can take if p greater or equal to less than plus infinity, h of xt equal g5 of x modulus of t p minus 2t plus g6 of x, with g5, g6 continuous on omega A, g5 of x greater or equal to 0, almost everywhere in omega A, g5 in W1 infinity omega A e g6 in W1 p minus 1 omega A. If p equal q, also the function ht equal t by 1 plus modulus of t satisfy this assumption. Then you can verify that this function satisfies all these assumptions. Just other two notation, we finish with in the sequel, f is a function in L p by p minus 1 omega. G is a function in W1p omega such that G is greater than 0 almost everywhere in omega A, and G the restriction of the trace of G on sigma A and on sigma 0 equals 0. Then G is a function defined in omega A, is 0 here and 0 here. And moreover, lambda is a real number. Then, which is the problem we're going to study? We're going to study these problems. Minus divergence of A of x gradient of u epsilon plus h0 dx u epsilon equal f in omega epsilon. U epsilon equal 0 on sigma A epsilon. U epsilon of x is less equal of g of x, and A of x gradient of u epsilon dot ni epsilon. Ni epsilon is the unit exterior normal vector to omega epsilon plus epsilon to power lambda h of x u epsilon less equal to 0 and u epsilon of x minus g of x a of x gradient of u epsilon ni epsilon plus epsilon to power lambda h of x u epsilon equal 0 on sigma a lateral epsilon. And finally, a of x gradient of u epsilon dot ni epsilon equal 0 on the boundary of omega epsilon minus the sigma a epsilon on sigma a lateral epsilon. Let us comment these problems. Then we have a problem on this, the omega epsilon, this domain with the strip. Okay? The question is divergence of ax gradient u epsilon. For instance, for simplify, you can assume a of x gradient u epsilon is equal gradient of u epsilon. Okay? Then here what do you have? Minus Laplacian of u epsilon. Simple case. H0 x u epsilon, for instance, you can take H0 equal 0 if you prefer. Then you have not this term. Equal f in omega epsilon. Moreover, we have some condition, boundary condition. We have u epsilon equal 0 on sigma a epsilon, then is 0 on the top of the teeth. We have this homogeneous nominal boundary condition everywhere except that on the top of the teeth and on the lateral boundary. We assume a Neumann homogeneous nominal boundary condition. What happens, what we ask on the lateral boundary of the teeth? That u epsilon is lesser or equal to this function g. We have fixed this function g. This is a fixed function. And also this condition is less than or equal to 0. Moreover, we ask that this product is equal to 0. That's what this means. That on the boundary condition, we have or u epsilon is equal to g. Or you have this condition is equal to g. But we don't know where we have the Dirichlet boundary condition and where we have the Neumann boundary condition. In general, we have this on this. Not both, because the problem could be not well posed, you have seen in the beginning of this course. Of course, in some case, if you consider minus delta u plus u equals 0, okay? In this u equals 0, you can add all the boundary conditions, the normal derivative equals 0 is well posed. But in general, you can choose this on this. Then, on this boundary, you don't know. In some parts, you have the Dirichlet boundary, u epsilon equals g. In other parts, you have this condition. If you take here h equals 0, you can take h equals 0. You have the Neumann boundary, homogeneous Neumann boundary condition. You can take h, I wrote it, h equals t. Then if you take h equals t, you have the Robin boundary condition. A of x gradient u epsilon, ni epsilon plus epsilon power lambda u epsilon equal 0. This is what we want to study. Why to choose this? This is called the Signorini boundary free boundary condition. Because some application, in chemical application, this U epsilon is a density. You don't know what happens inside the body. Then you want to know which condition you have. Okay, at first, it's not clear that this problem admits a classic solution. Then we want to work on a weak solution. And now I show you how we can obtain a weak solution from this problem, and we obtain an inequality, a variational inequality, not an equation. Weak formulation. Let us denote by cap epsilon the set of V in W1P omega epsilon such that V is less than G on sigma A lateral epsilon, and the restriction of V on sigma A epsilon equal 0. Then this is the set of function V in W1P omega epsilon such that V equals 0 on the top of the teeth, and in omega on the lateral boundary, the trace of V is less than the trace of G. So the weak formulation is that one. U epsilon in K epsilon. The integral on omega epsilon A of X gradient U epsilon gradient V minus U epsilon plus H0 di X U epsilon V minus U epsilon in the X plus the integral on sigma A lat epsilon H X U epsilon plus epsilon to power lambda V minus U epsilon in the sigma is greater than the integral on omega epsilon F V minus U epsilon in the X for every V in K epsilon. Just a remark that we had also this term, epsilon to power lambda, and epsilon go to 0. But it's clear the final result depends on lambda. A critical size will be lambda equal 1. We see later what happens. Okay, this is the weak formulation. I won't try to show how to obtain this formulation. Because you see, we have an inequality. This set is not a vectoral space. It is only a convex set. It's a closed convex set, but not a vectoral space. It also is not bounded. Okay? And this is the inequality, non-inequality. How to obtain? At first, we choose G0. The function G is defined only on omega E. But the trace of G on omega prime is 0. Then we can extend G by 0 on omega B, and we have a function in this function in W1P omega, in particular omega epsilon, is less than V is less than G by definition on sigma A lateral, and V equals 0 here. Let us choose in our problem as a test function No, multiply by u epsilon minus g. What do we do? We write like this. I write the divergence. Of course, let us assume that our problem admits a classical solution. That assume that all is regular, okay? That U is C2, A is regular, all is regular, such that our initial problem admits a regular solution. What do we do? Start from this point, divergence of A of x gradient of u epsilon start by this. Okay, divergence of Ax gradient of u epsilon minus g in the x. If we apply the Gauss theorem, this is equal the integral on the boundary of omega epsilon of what? A of x gradient u epsilon minus g d epsilon in the sigma. But on the boundary of omega epsilon, but the only part, what? The only part, on this part, you see, we have the Neumann homogeneous Neumann boundary condition. This is 0. Here, we have that this is 0. Then the only part is sigma A lat epsilon. Okay? This is equal the integral on omega epsilon, the divergence of A of x gradient of u epsilon minus g. I make the classical divergence of a product is divergence of the function gradient plus the integral on omega epsilon A of x gradient of u epsilon gradient of u epsilon minus g in the x. Okay? But this is equal the integral on omega epsilon, the divergence is equal f minus h0. Excuse me, it is minus. Minus then the divergence is equal h0 minus f. Okay? Then I can replace h0, the x u epsilon minus g in the x minus the integral on omega epsilon f u epsilon minus g on the x plus this term, the integral on omega epsilon a of x gradient of u epsilon gradient of u epsilon minus g in the x. Okay. Then this implies we obtain the integral on omega epsilon a gradient a of x gradient u epsilon gradient of u epsilon minus g in the x plus the integral on omega epsilon h0 of x u epsilon minus g plus equal this term ax gradient u epsilon. What is this term? From here, we obtain A of x gradient to epsilon ni epsilon product this is equal minus epsilon lambda h x to epsilon product this. Okay? When I can replace this. Done. Games. But it is on the right. I put on the left with the sign plus epsilon lambda, the integral on sigma a lateral epsilon h of x u epsilon minus g in the x equal, it's remain f, this term I put on the right, on omega epsilon f of u epsilon minus g. Then I obtained this equation. Okay? Do you agree? Can I? Did you copy? Okay. Then until now we have used this on the lateral boundary. This is the second boundary condition. Okay, we have to use that the first one. Did you copy? Huh?
Your literature on this topic had all the details of this. Your article on that topic had all the details, right?
Yes, the details of this one. Okay, can I? Can? Copy? Now, let us take V in this space. V in K epsilon. And let us choose, let us start from this point. The integral on omega epsilon divergence of A x gradient of U epsilon V minus g. Okay? As before, this is equal. We apply Gauss theorem, the integral on A of x gradient of U epsilon V minus g in scalar ni epsilon on sigma a lateral epsilon, only on the lateral boundary, because here that we have the homogeneous nominal boundary condition. Here, both is a function of 0. As before, we can write the integral on omega epsilon, the divergence of A of x gradient of U epsilon V minus g plus A of x gradient U epsilon gradient V minus g on the x. This is equal. As before, I recall that A is the solution of that problems. And then I replace divergence of Ax gradient U epsilon with this and this. Then is equal the integral on omega epsilon h0 dx U epsilon v minus g minus the integral on omega epsilon f v minus g plus the last term, the integral on omega epsilon a of x gradient of u epsilon gradient of v minus g in the x. The x. This implies, when we order it, we have then the integral on omega epsilon a of x gradient u epsilon gradient v minus g, the term of order 0 plus in the x, plus the integral on omega epsilon h0 x u epsilon v minus g is equal this term, the integral on sigma a lateral epsilon a of x h of x u epsilon v minus g dot in the sigma plus the integral on omega epsilon f v minus g. Okay, I rewrite this the term of order with the gradient of order 0. Here we have this term. Excuse me, this is a, not h. Sorry, a x gradient of v minus g scalar ni epsilon. Then we arrive to this equation. Can I delete this? G?
G to be non-negative.
Yes, G non-negative.
Why do we need that?
In the sequel, we have this assumption. Sometimes we use this. It's a technical assumption.
Can we relax that?
I don't know if it's possible. I suppose yes, but I'm not sure. Okay, what do we do now? We add to both terms this quantity plus the integral plus epsilon lambda, the integral on sigma a lateral epsilon, the h x u epsilon v minus g in the sigma. Here and also here we add. In the sigma, okay? We add on the left and on the right the same quantity. How we can write this? Let us see this part. How we can write this? This is equal the integral on sigma a lat epsilon of A of x gradient of u epsilon ni epsilon. Ni epsilon plus epsilon lambda h dx u epsilon v minus g in the sigma. Okay? Now what do? We know that v is less than g. Then this is less than 0. Now this condition, we have not used this condition. This is less than 0. Okay? Then this term is greater than 0. Okay? Then this integral is in the x is greater than the integral on omega epsilon f v minus g in the x. When finally we have just to then let us subtract this one from this one, and you obtain this variational inequality. Okay? Okay, then in the sequel, we can forget this problem completely. We work only with the weak formulation, but we have to prove that this problem admits a solution. The solution is unique, and then we can pass to the limit. At what time I started? At 12. I started. 30 minutes. Oh my God. No.
Too much.
No, a few times. Just 30 minutes I have.
Yeah.
Okay. I don't know how to. Okay. Some result, then I have no time to prove. Let u in W1P omega A epsilon. Then you can consider h u epsilon to sigma A lateral epsilon. You take u epsilon, you consider the trace of u epsilon on the lateral boundary, and you compute h. Or you can do also other things. This function, one can prove this function in L p by p minus 1 sigma A lateral epsilon by using our assumption on h. No, you take a function, you know u epsilon, sorry. Then we can prove that h u is in W11 omega A epsilon. This implies that h u, the trace on sigma A lateral epsilon is in L1 sigma A lateral epsilon. we have proved that, one proof that H of U sigma A lateral epsilon is equal H of U sigma A lateral epsilon almost everywhere on sigma A lateral epsilon. Then we have this lemma. You have U is in W1P omega A epsilon. Then you can consider the trace of U on the lateral boundary, and compose with the function H. The one proof that this is a function by virtue of the assumption of H in LP P minus 1 sigma A lateral epsilon. Okay? Moreover, you can consider H composed U. One can prove that this function in W11 omega A epsilon. Then this trace on the lateral boundary is in L1. Finally, we prove that this and this are equal, that you can commute the trace. I have not time, I'll give you the paper where this all is proved. Some actually result
This result is to make sense of
all also make a sense, yes.
to make sense of this variation.
Yes. Now in this equal you can see here as the H composed the trace, or you can see as the trace of a function. Sometimes one need one way, sometimes one need the other way, but it is the same, then we don't distinguish. A crucial result is the lemma that 2 days ago, last week, Patrizia Donato already exposed, to introduce a auxiliary problems. Let denote by Xi the unique solution of this, the unique weak solution of this problem. Laplacian Xi equal the measure of the boundary of omega prime, boundary of the measure of omega prime in omega prime. Gradient of Xi dot ni equal 1 on the boundary of omega prime, and the integral on omega prime, the y prime equal 0. Then you consider omega prime, I remind you, omega prime is in the unit cell, is the cross section to build the teeth. Then is in dimension n-1. In omega prime, you consider this problem. The Laplacian is, this is the measure, the perimeter of omega prime, and this is the Lebesgue measure of omega prime. We have this Neumann boundary condition on the boundary. Moreover, we have this condition because the solution is not unique. And if you, in your case, you can add this. In this way, the solution is unique. These problems admit a unique weak solution. But since we assumed that, we assumed in the beginning that omega prime has a regularity Cm with m greater than n-1/2. The regularity result ensures that this problem, the solution is not only weak, it's a classical solution, and the solution is C2. C2 until the boundary. Then C2 of the closure of omega prime. Then in the sequel, with this C, let us denote the sup modulus of gradient in omega prime. With this symbol, the sup of the maximum, this is a maximum of this set. There is this lemma. That this lemma is the lemma also Patrizia Donato Guibe. My idea was to prove it, but we have not time. Lemma. Let C be denoting also the 0, 1, n minus 1 periodic extension to the union of k in zeta n minus 1, the closure of prime plus k of the solution of this problem. Then epsilon, the integral on sigma a lateral epsilon v the sigma is equal to the measure of the boundary of omega prime on the boundary of omega prime, the integral on omega a epsilon v in the x plus epsilon, the integral on omega a epsilon gradient c x prime over epsilon dot gradient x prime v in the x for every v in W11 omega a epsilon. Then what you do? Take this function, okay? You have this cell. This is cell 0, 1, 0, 1. This is omega prime. You have this, C is defined in omega prime. And is the unique solution of this problem. Then extend by periodicity this by one periodicity in this domain. Okay? Then we denote this extension with the same name. Then for every v in W11 omega a epsilon, here, we have that epsilon, the integral of v on the lateral boundary, here, is equal this coefficient v omega a epsilon plus epsilon, the gradient of xi, computed in x prime by epsilon, inner product with the gradient with respect to the first n minus 1 variable of v only. I'm sorry, I have no time to prove this, because there is no time, but in the paper you have the proof. But it's the same result that Patrizia give you 2 days ago. Just another tool we have need, the Poincaré inequality. Since we have the function, this function have trace 0 here, we have the Poincaré inequality in this domain. The question is, when epsilon tends to 0, for each domain omega A epsilon, you have a constant. The Poincaré constant depends a priori on epsilon. We won't prove that really the constant does not depend on epsilon. Let us set W1P omega epsilon sigma A epsilon, the set of V in W1P omega A epsilon, such that the trace of V on sigma A epsilon equal to 0. Then the function in W1P omega epsilon, such that the trace is 0 here. We can prove that proposition. There exists a constant we call C Poincaré, okay, in 0 plus infinity. There exists epsilon 0 in 0, 1, such that the norm of U in LP omega epsilon is less than C point, the norm of gradient of U in LP omega epsilon for every U in W1P omega epsilon sigma A epsilon for each epsilon in 0 epsilon 0. The importance of this result is not that for fixed epsilon there is a constant, but this constant does not depend on epsilon, because you know in all the inequality, Poincaré inequality, Sobolev inequality, the constant depends on the domain. But we can prove that this constant does not depend on the domain. I have 10 minutes. I would like to prove, but maybe I need more than 10 minutes. Huh? Can I prove? Or huh?
You can start and next. You have many lectures, right?
Yes.
This is your first lecture, so
Yes.
why you are worried? Just stop it and then.
I have other things to do. Or maybe in the other lecture. Maybe in the afternoon they have the.
Yes, in the problem solving session.
In the afternoon we have problem time. Maybe if you want, I can prove this. It's just 15 minutes to prove this in the afternoon. Okay, then I have 10 minutes here. I can use for other things. It's precious at times. Which is the goal now? It's to prove that these problems admit solution and is unique. To do that, we have some functional spaces. Definition. Let V be a Banach space and let A from V to V prime. Then we have a Banach space A, a functional from V to its dual, V prime. We say that A is hemicontinuous by definition if and only if for each U1, U2, AV belonging to V, the function t belonging R assign A of U1 plus TV U2, this denoted duality belonging to R is continuous. Then what this means then? For every fixed U1, U2, and V, you consider this application T in R, assign A of U1 plus TV is an element of V prime. You compute on U2, you have a real number. This function, you ask this function is continuous. We say that I is strictly monotone only if for each U1, U2 in V, A U1 minus A of U2, U1 minus U2 is greater than 0. Poi equal 0 if and only if U1 equal U2. This is an element of V prime, you compute on an element of V. You would ask that is greater than to 0, and equal 0 if and only if U1 equal U2. Moreover, we say that A is coercive if and only if A U divided the norm of U go to plus infinity if the norm of U tends to plus infinity. A is bounded if and only if, by definition, A transform bounded set of V into bounded set of V prime. Okay? Then this definition of continuity, monotonicity, coercivity, and boundedness. Then we have this result that is proved in the book of Lyons, Quelques méthodes de résolution des problèmes aux limites non linéaires. Theorem. Let V be a separable and reflexive Banach space. Let A from V to V prime be coercive semi-continuous, bounded, and strictly monotone. let K contained in V be a closed and convex set. Let F belonging to the dual of V, V prime. Then there exists a unique U in K such that A of U V minus U is greater than F V minus U for every V in K. Then we have this abstract theorem proved by Lyons, in the book of Lyons. Then, just the last things, to prove the existence and uniqueness of these problems, we want to apply this result, which is the function, which is the space. We'll apply to the functional A epsilon W1P omega A sigma A epsilon, this space. No, we have defined some. This is a function with 0 on omega A in this dual. P which is a functional A U applied on V is equal the integral on omega epsilon A x gradient U gradient V plus H0 x U V in the x plus the integral on sigma A epsilon H the x UV plus epsilon lambda. This is the functional. Then we apply this result. This is the space. This is a functional. Our convex set is this one. When in the next lecture, we have proved that this functional satisfies is coercive and continuous, bounded, and strictly monotone. And we have the existence, the uniqueness, and also we have a priori estimates. We are able to obtain a priori estimates. Okay. If you want, we can meet in the afternoon. I give the proof of the node of the Poincare inequality. Thanks.